This lesson deals with a comparator and two applications of crossing detectors. You can find these notes in the course ebook in Chapter 8, starting on page 8. Suppose you take a real op-amp and sketch the output voltage versus the input voltage given a power supply. The output would look something like this. For a given input, the output would be increasing when the input's positive and then stop at a voltage we're going to call Vset positive. And this is roughly the positive power supply. If the voltage Vin goes negative, it starts to decrease at the output and eventually stops at the negative power supply, which we're going to call minus Vset minus. The reason I have the values here is that Vset positive is usually a little bit smaller than VCC, and minus Vset minus in magnitude is a little bit smaller than the magnitude of minus VCC. These op-amps have a gain, and we can calculate the gain as the change in output voltage over the change in input voltage. For most op-amps, this is around 200,000 volts per volt. And what that means is that if we clip or saturate at 15 volts, and you divide that by 200,000, V sub x is 75 microvolts. And what that means is that whenever this voltage is greater than 75 microvolts, the output just stops at the positive power supply. If you take minus 15 volts and divide it by 200,000, you get minus 75 microvolts. So when this voltage is minus 75 microvolts or more negative, the output stops at minus 15 volts. If we're using plus and minus 15 volt supplies. So if we operate this op-amp without feedback, it takes a very small positive voltage for it to saturate positively, and likewise a very small negative voltage for it to saturate negatively. An op-amp that's used this way we're going to call a comparator. We can define an ideal comparator as having the following property. The output is the positive saturation voltage when the input is greater than 0, and it's the negative saturation voltage when it's less than 0. Take a look at an application called an inverting crossing detector. To analyze these types of circuits, what you need to do is label where Vin is, and then solve for Vin in terms of the inputs to your circuit and the other circuit components. So here I've got a battery connected from the plus terminal to ground, and the voltage V1 is a rise in voltage, Vin is a rise in voltage, and then the drop would be V sub R. So we can then solve for Vn as V sub R minus V1. When this quantity is positive, then the output will saturate positively, and that means that V1 would be less than V sub R. So whenever our input voltage, which could be something changing with time, is less than a DC value, the output will saturate positively. Likewise, the output will saturate negatively when this equation is negative. That would mean that V1 is greater than V sub R. We could graph that. Let's assume that V sub R is a positive voltage, and I'll sketch the input and the output. And whenever the input is less than V sub R, the output saturates positively. Likewise, when the input is greater than V sub R, the output will saturate negatively. This is called a crossing detector because we're detecting when the input voltage crosses the value of V sub R. Inverting is used here in the sense as V1 increases, V2 saturates negatively. If there's an inverting crossing detector, it would seem reasonable there's a non-inverting crossing detector, and it's shown here, where the plus sign is on the top and the minus is on the bottom of the comparator. Label where Vin is, and now let's solve for Vin in terms of my input and my reference voltage. Rise in voltage is V1, the drop is Vn plus V sub R. So Vn is equal to V1 minus V sub R. So when this quantity is positive, the output saturates positively. That would mean that V1 is greater than V sub R. Showed over here on a graph of V1 and V2 that whenever V1 is greater than V sub R, the output saturates positively. Likewise, when this quantity is less than 0, the output will saturate negatively. That would mean that V1 is less than V sub R. Here showing is V sub R, and when I'm less than that, I saturate negatively. V sub R can be positive or negative, and it can be 0. And we can create the voltage V sub R by taking a voltage divider from our power supplies. We can create a positive or a negative voltage that way. Let's take a look at some lab data. Using a 4 volt, 2 kilohertz sine wave with a plus and minus 15 volt power supply. Suppose my reference voltage is 3 volts. So here's a graph of my voltage V1, has a period of 1 over 2k or half a millisecond, goes up to plus 4 and then down to minus 4. Here's where 3 volts is, marked it on this plot. And whenever the input is greater than 3 volts, the output saturates positively. Likewise here, here, and here. And then when it's below that, it saturates negatively. So all below here we're minus 15 roughly, and then minus 15, and so on. Notice there's a little bit of an indentation over here. That's because I'm using an actual comparator, and you do get some distortion due to the non-ideal effects. And this is how a comparator works and two crossing detector applications.